Hello, 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 hello. So today's topic is forced oscillator. So already we have completed the simple harmonic oscillator, which is also called as undamped oscillator. So that is nothing but simple harmonic oscillator means it is undamped. Okay, so undamped oscillator. Undamped oscillator means the amplitude of the oscillator is going to be independent of time. So this is nothing but the equation of motion of a simple harmonic oscillator. Okay, where small a is called as amplitude. So this amplitude is independent of time. So here the amplitude it does not depend on time. So it is independent of time. Nothing but if once the oscillator is going to be continuing its oscillation, so those oscillations will be continued forever. So it will not decrease with respect to time. So that is called as simple harmonic oscillator or undamped oscillator. But when you are going to do the experiment, for example, if it is a simple harmonic oscillator or simple pendulum, so one of the example for simple harmonic oscillator is nothing but simple pendulum. Okay. But when you are doing this simple pendulum experiment, the amplitude of the simple pendulum are going to be slowly decreasing with respect to time. That is because of friction of air medium. So simple harmonic oscillator means it is an oscillator in which the amplitude is going to be constant. It does not depend on time. But in reality, when oscillator is going to make some oscillations, so because of friction of the air medium, so the amplitude is going to be slowly decreasing. So those are called as damped oscillations. Okay, so damped oscillations. So in case of a damped oscillator, the equation of motion is given by a into e to the power minus bt sine omega t plus phi. So here you can see this is nothing but the amplitude a into e to the power minus bt. That means the amplitude of the oscillator depends on time and it is exponentially decreases. Okay, whereas in case of a simple harmonic oscillator, the amplitude, the equation of motion is given by y equal to a sine omega t plus phi, where a is nothing but amplitude which does not depend on time. So in case of simple harmonic motion or simple harmonic oscillator, the amplitude remains constant, but because of friction of the air medium, the amplitude is going to be slowly decreasing. That is called as a damped oscillator. So here you can see this is nothing but the amplitude a into e to the power minus bt, which is a function of time. That means the amplitude is going to be decreasing with respect to time. Okay, so first of all we have simple harmonic oscillator where amplitude is going to be constant, but because of the medium friction, okay, the amplitude is going to be slowly decreasing. Okay, that is called as the damped oscillator. Okay, so in order to retain the oscillations of the oscillator to the initial, okay, that is nothing but undamped. Okay, so for example, this is nothing but simple harmonic oscillator. Okay, so as per the definition, simple harmonic oscillator amplitude should be constant. So here the amplitude of the simple harmonic oscillator should be constant. It does not depend on time. But because of the presence of air medium, so the simple pendulum or the simple harmonic oscillator is going to experience a frictional force. So because of this frictional force, the amplitude is going to be slowly decreasing. That is called as a damped oscillator. So in order to maintain the amplitude as constant, even in the presence of frictional force, so we have to apply a periodical force. So here I am going to apply a periodical force. Then it is going to make one complete oscillation. Then again I am going to apply force. Then one complete oscillation. Then one complete oscillation. So in order to get the initial undamped oscillations, so we have to apply some periodical force on the damped oscillator. Therefore you will be moving to again back to simple harmonic oscillator. So in case of forced oscillator, so first of all it is basically a undamped oscillator where the amplitude is going to be constant. So that is given by the force acting on the simple pendulum is nothing but F equal to minus mu x, or sometimes it is maybe minus kx, so which is called as a restoring force. Okay, nothing but at the same time, so in case of damped oscillator, so the frictional force is going to be acting. So the frictional force, the factor which is related to frictional force, so that is given by minus r dx by dt. So where r is called nothing but r is related to frictional force constant. So in case of forced oscillator, we have to apply the periodical force, external periodical force. So here I am going to apply some external periodical force. So this is called as the external periodical force. So okay, the net force acting on the oscillator in case of simple nothing but in case of forced oscillator, so that is minus mu x. So this is the force in case of undamped oscillator. Along with minus mu x, the second term. So this is the case of a damped oscillator. So in order to improve the oscillations, of a damped oscillator toward the undamped harmonic oscillator, we have to apply some external periodical force. So that is given by the third term. Okay. So this force can be written as according to Newton law, m into d square x by dt square equal to minus mu x minus r, okay, dx by dt plus capital F into sin pt minus theta, or you can write m into d square x by dt square plus mu x plus r into dx by dt, okay, which is equal to capital F sin pt minus theta. Or the same expression you can write d square x by dt square plus mu by m x plus r by m dx by dt equal to capital F by m sin pt minus theta. Okay. So here I am going to take 2b as r by m and omega square equals to let mu by m and small f equal to capital F by m. Okay. So I am going to rearrange this equation. So d square x by dt square plus, so here r by m is nothing but 2b. So 2b dx by dt, okay, plus mu by m is nothing but omega square. So omega square x equal to, okay, capital F by m is nothing but small f sin of pt minus theta. So let this one is nothing but equation number 1. So this equation number 1 is going to represent the differential form of a simple, forced oscillator. Okay. So I am going to take the solution of this equation. Okay. Let the solution of this equation. Okay. Because every differential equation is going to have a particular solution. Okay. So here also I am going to have, I am going to take a solution. So initial phase, here you can take initial phase at theta. So directly I am going to take, for example, if it is pt only. Okay. So the solution of this equation is nothing but x equals to capital A into, for example, if it is sin pt minus, here I am going to take the phase. Okay. So x equal to A sin pt minus theta. So here I have to substitute the solution this equation. So for this purpose I need first order derivative and second order derivative. Therefore dx by dt equals to capital A, differentiation of sin is nothing but cos. So cos of pt minus theta. So here differentiation is with respect to t. Therefore p will be treated as constant. Therefore p. Similarly d square x by dt square equals to a into p. Differentiation of cos is nothing but minus sin. So minus sin pt minus theta. So differentiation is with respect to t only. Therefore p will be constant. So here again one more p. So p square. So substitute these values. Okay, in equation number 1. So I am going to substitute these values in equation number 1. So d square x by dt square. So that is nothing but minus ap square sin of pt minus theta, okay, then plus 2b dx by dt value, so ap cos pt minus theta, okay, plus omega square, then we have x value a sin pt minus theta, which is equals to f sin pt. Okay, so here I am going to slightly change the right hand side. Okay, this f sin pt, so it can be written as f sin pt minus theta, this is one term, plus theta. Okay, so minus theta plus theta gets cancelled, therefore there is no change. Okay, so which is equals to f into, so this is similar to that of sin a plus b. Okay, so we can apply sin a plus b formula. Okay, so here sin of a plus b means, so pt minus theta cos theta plus, okay, cos pt minus theta and sin theta. Okay, so this is nothing but right hand side. Okay, f sin pt, so we have rearranged this one, this is nothing but left hand side, this is nothing but right hand side. Okay, so again I am going to write over here, so minus ap square sin pt minus theta plus 2bp ap 2b ap cos pt minus theta plus omega square a sin pt minus theta, which is equals to, so small f into sin pt minus theta cos theta plus cos pt minus theta and sin. Okay, so here I am going to compare the terms which are related to sin pt minus theta. So first of all I am going to compare the terms which are related to sin pt minus theta on both sides. Okay, so this is nothing but one term on left hand side, so here we have another term on left hand side, therefore minus ap square, the quotient of sin pt minus theta minus ap square, okay, plus omega square a equals to, so here on right hand side f cos theta, so I am going to take this one as equation number 2. Okay, similarly again I am going to compare the cos pt minus theta term on both sides. So here we have only one term on left hand side, so 2b ap equals to, so on right hand side, so here we have f sin theta, so this is equation number 3. Okay, so now I am going to square these two equations and add, so equation number 2 square plus equation number 3 square. Okay, so I am going to square these two equations, then I am going to add. Okay, so in both cases we have a as common, so you can write a square. Okay, so here omega square minus e square whole square, so this is nothing but square of equation number 2 left hand side. Similarly plus 4b square a square p square. Okay, so that is on for equation number 3, square of equation number 3, okay, left hand side. So adding plus, which is equals to, so here from equation number 2 right hand side f square cos square theta plus f square sin square theta. If I take f square as common, so it will be cos square theta plus sin square theta, that will be equal to 1. So directly I am going to write small f square only. Okay. So this is nothing but the final one. So from this equation I would like to get amplitude. So amplitude is given by, so here a square, here equal to, again I mean here both in the both terms we have a square, so here you can take a square as common. So capital nothing but small f divided by under root of, okay, omega square minus p square whole square plus, okay, 4 b square p square. Okay, so this is nothing but the resultant amplitude. Okay, so resultant amplitude of the forced oscillator. Okay. Similarly, suppose if I want to get the phase difference, so from equation number 2 and 3, if I divide equation number 3 by equation number 2, okay, equation number 3 divided by equation number 2 means sin theta divided by cos theta. So that is nothing but tan theta equals to, okay, so tan theta equals to 2BAP, okay, divided by A into omega square minus p square. Okay, so numerator A, we have denominator A, therefore this is nothing but 2BP divided by omega square minus p square. Therefore you can write the phase difference equals to tan inverse of 2BP divided by omega square minus p square. Okay, so this is nothing but the phase difference theta equals to, and this is nothing but the resultant amplitude of the forced oscillator. So I am going to write the equation of motion right now. So the equation of motion of a oscillator, okay, so that is given by y equals to capital A. So where capital A is nothing but this one, okay, so f divided by under root of omega square minus p square, okay, whole square plus 4b square p square, okay, sine of it is p theta minus t. So already we have taken pt minus, pt minus t, so sine of pt minus theta. So where theta is nothing but tan inverse of 2bp divided by omega square minus p square. Okay, so this is nothing but the resultant equation of motion of a simple harmonic oscillator. So where this is nothing but the amplitude. Okay, so this is nothing but the amplitude of the forced oscillator, where the amplitude depends on small p. Okay, so amplitude depends on small p. So this is nothing but we have taken the external force f sin pt. Nothing but small p is nothing but the angular, the frequency related to external applied force. Okay. Similarly, the amplitude of the forced oscillator, it also depends on B. Okay, so it also depends on B, where we have taken B nothing but 2B equal to R by M. So R is nothing but it is related to quotient of frictional force. So in case of forced oscillator, the amplitude of the forced oscillator depends on applied external force frequency as well as the frictional force constant. Okay, so depending on the values of omega and p, nothing but either omega square is greater or omega square is less than, or both becomes equal. So depending on these three cases, we will be having three cases. So we will start from case number 1. Okay, so case number 1 means, so here just wait. So case number 1 means if external, okay, if the frequency of external force P, okay, so this is nothing but P is nothing but the force, nothing but the frequency, angular frequency of the external force is less than the natural frequency of the oscillator, okay, then, okay, so from this equation P is very small, therefore you can neglect P square here, Okay, therefore the amplitude now becomes equals to, the amplitude is nothing but actually f divided by omega square minus p square, okay, whole square plus 4b square p square. Okay, so in this case p is very small, therefore you can neglect here p square, here also p square. So just only you have f divided by omega square to the power of 2, nothing but omega to the power of 4 square, nothing but just only omega square. Okay, so so in this case you can see when the applied force frequency, when the applied force frequency, periodical force frequency is less than the natural frequency of the oscillator, the resultant amplitude of the forced oscillator depends on its natural frequency omega only, it does not depend on external force. Okay, similarly we will be moving to case number 2. So case number 2 is nothing but the applied force frequency and the natural frequency are both becomes equal. Then what will happen we will see here. So the resultant amplitude is nothing but capital A equal to f divided by under root of omega square minus p square whole square plus 4b square p square. Okay, so here p equal to omega, nothing but there will be no first term. Okay, just only 4b square p square. Therefore the resultant amplitude becomes equal to 2bp. Okay, f divided by under root of 4b square p square, nothing but f divided by 4bp. So that means it depends. Okay, it depends on the applied external okay, applied force frequency. Here I am going to write. So amplitude. So amplitude, template A of the forced oscillator, okay, depends on, okay, depends on P. So what is P? Applied, okay, force frequency. The frequency of external applied force, as well as it also depends on B. Okay, so B is nothing but it is related to friction of the medium. Okay, so in this case the amplitude of the forced oscillator, it does not depend on oscillator natural frequency, it depends on applied frequency, force frequency as well as B value. Okay, then I will be going to the last case. So that is case number 3. So if the applied force frequency, okay, is very much larger when comparing with the natural frequency of the oscillator. Okay, so what will happen? So here we can see the amplitude is given by, okay, f divided by again omega square minus p square whole square plus 4b square p square. Okay, so this is nothing but the amplitude of the forced oscillator where the applied force frequency is very much larger. Okay, so here I can neglect the value of omega square because it is very small when comparing with p square. Okay, so minus p square to the power of 2 that is nothing but p to the power of 4. Okay, so here p to the power of 4, p to the power of wait, actually here we have taken omega square minus p square whole square, right? Okay, so when p is large means you can neglect omega square, so p square to the power of 2 is nothing but p to the power of 4. Okay, p to the power of 4. So again you can neglect b because b is related to the force constant, frictional force constant. So if I remove this one, so it is purely depends on, okay, applied frequency only, applied force frequency. Okay, so this is about forced oscillator.